All right, can someone tell me, can you hear me?
Yes, we can hear you.
I don't know, my computer tells me my microphone isn't working, so I get nervous. All right, good that you can hear me. We'll begin momentarily. In the meantime, the code for today is 9575. Let's put that in the chat. So Top Hat code for today is 9575. So our agenda for today is we're going to start our discussion of sorting. Sorting will take us into next class as well. We will have a second lecture on sorting, and sorting will also be important in many other topics. So order statistics, which is the next topic after that, relies heavily on the sorting algorithms we're going to discuss today and Monday. And then many other algorithms, computational geometry, many of the algorithms there are similar to things we will learn in sorting. So sorting is really very important, and we'll keep referring back to sorting up until the very end of the semester. When we do parallel algorithms, we're going to revisit some of these sorting algorithms from a parallel perspective. Okay, so with that, and then towards the end of class, we're going to go back and finish up that assignment on searching algorithms. So we had a few things to wrap up there. So let me share my screen. And you will notice that I posted some review questions for lecture number 1 in the Top Hat on the introductory material, and I will regularly be posting some review questions there. Okay, so everyone can see my screen. You see that little toy that you may have played with, something like it when you were a baby? Everyone see that? Yes. You see that. Okay, very good. All right, so today we're going to start our discussion of sorting algorithms. And as an introductory question, why do so many algorithms courses or even data structures courses, why do they all seem to talk about sorting? And one answer is simply it's a real world application. It's not just something theoretical that some computer scientists thought of. We all need to sort things. We sort papers. We sort place cards for a wedding or a special event, right? We always need that. We sort books in order. We sort things. So we want to know, when we're sorting a lot of things, what are the efficient ways of doing that? Number 2, many other algorithms, this is more from a computer science perspective now, many other algorithms rely on sorting. So yesterday when we did our searching code, someone reminded me we had to flip that switch to say sorted equals true, because many of the search algorithms require that the data be sorted first. In graph algorithms, all right, we need to sort the data first. So Kruskal's minimum spanning tree algorithm, we need to sort the data. We need to sort the edges in increasing order. Greedy algorithms, we need to sort the items in the knapsack and value over weight, right? So a lot of algorithms require that we sort them. Or the algorithms themselves, not just that we need to sort it as a prerequisite, but the actual solution to the problem will mirror ways in which we sort. All right, so again, it comes up in a lot of other ways, but here's another reason as well, and that is that the techniques that we want to learn in this class about analysis of algorithms, this is of course in the design analysis of algorithms, so many of the techniques we have for design come up in sorting, and many of the techniques we have for analysis come up in sorting. So it's a good way to learn these broader skills that are important in this course. All right, so when we talk about sorting, there are a number of words that continue to come up, so we want to be sure that we understand what these mean. All right, one of them is an inversion. An inversion means that data is out of order. Okay, so more specifically, let's say you have an array and we're looking at a earlier data element versus a later one. We would expect the earlier ones to be smaller. If they are out of order, we call that an inversion. And what is a swap? What's the purpose of a swap? Swap is to remove the inversion, right? So we have two elements that are out of order. We flip them around. And by the way, in Python, you can do that in one line. Typical algorithms will show you 3 lines to do that, but in Python, you can do that in one line of code, right? So you can remove an inversion. Now, when you talk about sorting algorithms, we have in place and out of place. In place means that it keeps the data within the array itself. So an example of that is bubble sort, selection sort, and search and sort. We don't need any extra data to do the sorting. Out of place means we need additional storage to do it. Can anyone give me an example of a algorithm that is out of place, meaning it requires additional storage, not just one variable, like an entire array for sorting?
Merge sort.
Which one?
Merge.
Merge sort, correct, merge sort. Okay, heap sort, if it's done right, can be done in place. Okay, usually it's done in place. Stable sort, so a stable sort is not the name of a sort, it's a feature, right? Some sorts preserve order that is already there, meaning if two data elements are not inverted, they will never become inverted with respect to each other. Some sorts are not stable. For example, selection sort. Selection sort is a very basic sort, but it is not stable. It means that sometimes you have something that's out of order, that is in order, but it will move it around temporarily to do what it needs to do. All right, we have a sentinel. Sentinel is a marker that's put in the data, but it's not part of the actual data. Anyone know which algorithm? Maybe you learned this in data structures or elsewhere. Which simple algorithm often uses a sentinel? Not always.
Would that be quicksort?
Does quicksort use a sentinel? I don't know. I think the data that's in there is, it's all the data itself. So the example that comes to mind is insertion sort. Sometimes we put an extra element that's not really part of the data in the first position to make sure we don't go out of bounds, right? An offline algorithm, okay, this will come up later on again in when we talk about bucket, not bucket sort, sorry. We talk about approximation algorithms for, not the bucket, what is it called? The bin packing problem. Right, so offline means we have all the data up front. Okay, so typically when we sort things, someone gives us all the data and says sort it. But in real life, things don't always work like that. Why not? Think about, you're working in FedEx or UPS or USPS, and you're, putting boxes onto trucks.
New elements keep coming as you're trying.
Yeah, you have some kind of assembly line where the packages are coming as we speak, right? And you got to figure out, okay, where does it go? Which truck do I put it in? Where do I put it in the pile, right? So the data is coming as we're processing it, okay? So that's, again, the algorithms we're going to study in sorting tend to be offline algorithms, but there are online ones that I know one of the chapters in the Xi book deals with that as well. Comparison-based sorts, that's another thing. Okay, the sorts we're going to do today are all comparison-based sorts. We look at two elements, we compare them, and we make decisions based on that. Can anyone give me an example of a sort that is not comparison-based, meaning we sort without taking one element and comparing it to another element?
Radix sort.
Okay, radix sort is an interesting one. It's sort of it's a little bit of a hybrid, but yes, it uses a non-comparison based approach behind the scenes. Good. Counting sort. Okay, so counting sort is really a pure non-comparison based sort, right? It's just looking at the data itself, and it's using that to figure out how to get the data in order. Okay, but again, today will be comparison-based sorts. All right, so how do we one of the things we like to do in this course is we like to organize algorithms into groups. So we can organize algorithms in general, but more specifically sorting algorithms by their time complexity. Remember what time complexity is? It's not the actual time on the clock. It is the order of the number of operations relative to the size of the data. So we are going to group them into very big groups. Okay, first we have linear time. Okay, in the bottom. Okay, linear time means that the amount of work is proportional, directly proportional to the amount of data. Okay, now, generally speaking, we can't get linear time. Someone mentioned radix sorts, right? Radix sort is sort of linear, but there are assumptions. You see my boat there makes assumptions about the data. What assumptions do we make about the data in radix sort? So an assumption we make about the data is that the number of digits is fixed, right? So maybe it's a decimal number, but they're at most 2 decimal places or 3 decimal places, right? If it's arbitrary precision, then we're not going to be able to get the linear time, right? Then we have linear arithmetic, which we said is another word for n log n, right? We have a whole bunch of sorting algorithms in that category, right? We have merge sort, we have heap sort, we have quick sort in the average case, right? So we have a bunch of algorithms in that category. Then we have polynomial time algorithms, all right? Things like a bubble sort, which is n squared, selection sort, which is n squared, shell sort, which may be like n to the 3/2 or n to the 4/3 or n to the 1.5, right? Depending on which version you have and what analysis you're doing on it. And then we have super polynomial. Super polynomial means, what does little omega mean again? Anyone remember? Can tell us what little omega means? The little omega means bounded below, strictly below. So what we're saying is there are some algorithms that take more than polynomial time. Anyone know of an example of that? A sorting algorithm that takes more than polynomial time. Okay, there is something called Stooge sort, and we'll see that soon. Okay, so these are some of the classic sorting algorithms. We will get through approximately half of them today, and the other half we'll look at next time. All right, so our first algorithm is a BOGO sort. All right, I don't know exactly what a BOGO is, but it doesn't connote someone who's particularly intelligent. And the way the BOGO sort works is you permute the data randomly, and then you check if it's sorted, right? If it's sorted, then you're done. If it's not sorted, then you're not done. All right, this is a Las Vegas algorithm. Las Vegas algorithm means there's probability involved, randomization involved, and it will always give you the right answer. It's just we don't know how long it's going to take. Okay, so this one could take a very long time. Why might it take a very long time? Because it may not get the permutation that works for a very long time. Okay, so here's the code for it. Notice that we need to randomize the data. So we have our own little shuffle program here. And we have a little graphic, okay? So Winnie the Pooh says, well, I'm going to compare merge sort to BOGO sort. It says BOGO sort is better. You know why? Because merge sort takes at least n log n, and BOGO sort takes at least n. Okay, what's the problem with Winnie the Pooh's argument? What mistake is Winnie the Pooh making?
BOGO sort could take much longer than n.
BOGO sort can take, so it is bounded below by n, but that's a best case scenario, right? It could take, how long could it take? It actually take infinity time. It may never actually come up with the correct permutation. It may get unlucky, but on average, it actually will take n factorial, which is ridiculously slow when you could sort, conclusively and complete the job in n log n. All right, so that's not a very good sort. In fact, I only learned about it a few years ago from one of my students in class, but I was not familiar with it because there's no reason to learn BOGO sort. It's not really useful. All right, we have a bubble sort. All right, so bubble sort is not really used much in practice, but it does set the stage for some of the more realistic algorithms. And the basic strategy of bubble sort is we look at successive elements of the array and we compare them. And we say if they are out of order with respect to each other, what's called an inversion, right? So the one in position 5 is bigger than the one in position 6, we swap them. All right. Anyone know why it's called bubble sort? What does it have to do with bubbles?
Bubbles of numbers kind of rise up to the beginning. Or end.
Okay, so just like I have a bottle of water here, it would be better if I had seltzer because you can actually see the bubbles. But just like in seltzer, the bubbles rise up to the top and the heavier water goes down to the bottom. So similarly, the light elements rise up to the front of the array and the heavy ones go to the bottom. Now, of course, a lot of bubble sorts really work like that. They just get to that point differently, right? Now, this is an example of a decrease and conquer by one algorithm, right? So that's the design strategy. So one of the goals of this course, one of the objectives is to teach you not only algorithms, but also design strategy. So it's called decrease and conquer by one, because at each main iteration, the outer loop, we reduce the problem size by one. Why? Because the largest element is now in the last position. So it's out of the picture now. Now the next iteration, the second to last element is out of the, okay, just one second. If I answer this question, then your thing will get converted more quickly. So I just need to say, okay, and then it can, there we go. All right, so that's what we call decrease and conquer by one, and it can be done recursively or non-recursively. So here is an illustration of what happens in bubble sort. Look at the light blue. Right? The light blue is the two elements that we're focused on, and we compare them with each other. And if they are out of order with respect to each other, we swap them. If they are in order with respect to each other, let's say the 6 and the 8, then we don't swap them. The 8 stays where it is, right? Now, if you look at each group, each separate picture, you'll see that in this picture here, the green, the last column, the last element 8 is in its final position. So the green means it's done. Right? At this point, the last 2 elements are done. At this point, the last 3 elements are done. At this point, the last 4 elements are done, and gradually you get there until everything is done. Okay, so that's bubble sort. Here is the basic code for bubble sort. Now, bubble sort is slow. We'll talk about how slow it is in a moment, but there's something we can do to make it a little bit faster. And that is that if we observe that we got through the array and we didn't swap anything, what does that tell us?
It's already in order.
It's what?
It's already in order.
It's already in order, right? So if we make a pass through the array and everything was always bigger than the thing before it, then it's already sorted. So in some versions of bubble sort, let's see if I have a code for that. No, I don't have a code for that. But in some versions of bubble sort, we have a early exit criteria. In a few minutes, we're going to learn cocktail shaker sort, and cocktail shaker sort actually is designed like bubble sort, and it has that extra modification in there. But first, we're going to sort of prove that bubble sort works. Okay. And if you remember how proof by mathematical induction works, so we have a base case and we have an inductive hypothesis where we assume something is true, and then we use that to prove the next case. So here's what we're going to do. We're going to start with our base case. When there are 0 elements, or 1 element for that matter, in a array, Y is already sorted, meaning the bubble sort works without doing anything. Y is an array with 1 element already sorted.
There's nowhere else for the element to go. It's just one
There's
element.
nowhere else for it to go. Okay, so that part is sort of obvious. All right, now we're going to assume, we're going to do an inductive hypothesis here, and we're going to assume that the bubble sort works for some value. Okay, meaning if there are k minus 1 elements, it works. So we have to show that it works for n equals k. So here's what we do. We say, okay, let's move the largest element to the last position. Do we agree that bubble sort does that? Yeah, because it keeps comparing that element with the one next to it. And if it's bigger, they swap positions. So as we go through the loop, the very last position is going to have that biggest element. Now what do we have left? We have k minus 1 elements to focus on, and via the inductive hypothesis, bubble sort works on k minus 1 element. So therefore we prove that bubble sort works. Okay, now we get to the analysis. So if I asked you, I think most of you would know at this point that bubble sort is an n squared algorithm. The question is, how do we get that? So we say as follows. The first time through, how many comparisons did we have to do?
N minus,
N minus 1, right? Because we're comparing each thing with the thing before it. So for the first element, we don't need to compare it to anything. The second element, you compare to the first. Third, we compare with the second, and so on and so forth. So you have N minus 1 comparisons. Then we have N minus 2 comparisons, N minus 3 comparisons, so on and so forth. And we add all that up. What do we get?
N times minus 1/2.
N times N minus 1 divided by 2. Everyone remember Gauss? I think I had that in a slide in a previous lecture. So if you're not familiar with that, let's just put that in here. Okay, so if you haven't, I imagine you've all seen this before. 1 plus 2 plus 3 plus ... plus N. Okay, we have that. And we have, say this as forwards. And then, you've seen this before, but just in case not. Okay. Hold on. And if we do it backwards, okay, so we're taking the same sum and we're writing it backwards. Okay, what do we get? So we get N plus 1 plus N plus 1, right? So each pair of terms, plus N plus 1. So we just make a comment here. Right, and what do we get? So we have N times N plus 1 equals N terms of N plus 1 each. And then we get N times N plus 1 divided by 2, divide by 2, because we only have 2 equations, not 1. Okay, so that's how we got that. Okay, so let's come back here. Now, the number of comparisons doesn't change, but why do the number of swaps change between the worst case, average case, and best case?
If it's already in order, doesn't have to swap anything, and if it's totally
Okay, so if it's already in order, that's the best case, then we never have a swap. We're going to do comparisons, but we never swap anything. So that's where this 0 comes from. And what about this? This is probably the least obvious of the three. So on average, we would expect that half of the comparisons result in swaps on average, right? So if the total number of comparisons, as we just established, is N times N minus 1 divided by 2, then if we take half of that, we get N times N minus 1 divided by 4, which is also order of N squared. It's just a smaller function. All right. Now, as I mentioned before, there is a variation of bubble sort where we stop early if we find that we did it. So it's still going to be N squared. Comparisons, the best case goes down to N, because if we, for example, on the first pass through or the second pass through, we determine that it's now sorted, we can exit early. So it can be still be order of N. The swaps Worse than average is still going to be n squared, but the best case is still 0 as it was before. Okay, so that's what we just talked about. All right, so let's take a look at cocktail shaker sort. So there are two things I want you to see about this cocktail shaker sort. Number one is that we have our outer loop as we did before, but we have one loop, inner loop here, and a second inner loop here. So first, can anyone tell us why we have two inner loops? And I'll give you a hint, look at the range. So range in Python is, telling you where to start and when to end. So look at the range here. And look at the range there. And what can you tell me about the two ranges compared to each other?
It's shifted to the left by 1.
Well, more generally, right? So the range doesn't actually shift. What is changing? Where does the first loop start?
Start,
And where does it end?
end,
And where does the second loop start?
-1,
N minus 1, where does it end?
start -1.
Good. And which direction is it going?
Down the list, so to speak.
Backwards. It's going backwards, right? The first one's going forwards and the other one's going backwards. So that's the difference. We have two loops. One goes forwards and one goes backwards. When I was at your age, so the printers were dot matrix printers, and it printed from left to right, and then it would go back to the beginning of the line like a typewriter, and then it would print another line. And then someone got smart and they said, hey, why doesn't it print when it goes from left to right and when it goes from right to left to right, right to left? That's what this algorithm is doing. All right. The other thing it's doing is what we mentioned before, but you didn't actually see as code, is it checks. Okay, it says, did I do any swaps in that loop? If I did a swap, then continue. But if I didn't do any swap, if swap equals false, then I'm going to break. Break means exit, right? Same thing down over here, except we don't need to make a check because the check is implied by the outer while loop as well. Okay, so there are really two changes in the cocktail shaker sort. Number one is the thing we already talked about in bubble sort, but we didn't actually do, which was to exit early if we find that it's in order. And the second thing is to go from left to right and from right to left, both ways. What does cocktail shaker sort do? What's its advantage? Its advantage is that it gets big and small elements out of the way very quickly, so they don't cause us any problems. So the small elements move to the left right away, the large elements move to the right away. So if you have some extreme elements, they're not going to be in your way and cause things to slow down. Anyone know why it's called a cocktail sort or cocktail shaker sort? Oh, here you see a picture. You see how we're getting the large elements, on one end and the small elements on the other end. Bubble sort, it's always the large elements on one end and gradually you get to the other. Here you take turns. Anyone know why it's called a cocktail sort? So maybe none of you go to the bar, and that's not necessarily a bad thing. But what is a cocktail in a bar? You don't have to go to the bar to drink a cocktail. What is a cocktail?
Type of drink?
Mixed drinks.
It's a mixed drink, right? Or you could have a cocktail fruit salad, right? Fruit cocktail. So it's a bunch of things mixed together. Now, not true of a fruit cocktail, but in a bar, if they make a cocktail, what do they need to do? How do they mix it? So today they use some kind of blender and they press a button. What did they do in the good old days?
Like shake upside
They
down.
shake it. They go like this, right? Back and forth, back and forth. So that's why it's called a cocktail sort, because the going back and forth, back and forth. Okay, that's where the name comes from. All right, we're ready for our fourth sort, right? So far we had BOGO sort, which is pretty bad. We had the bubble sort, not quite as bad, but not so good either. We had the cocktail sort, and now we have our selection sort. So selection sort is called selection sort because we select the largest element and we put it in the last position. We select the largest element and we put it in the second to last position. Or you could write it differently. You could select the smallest element and put it in the first position. Select the second smallest and put it in the second position. That's why it's called selection sort. In a certain sense, bubble sort is also like that, but it doesn't immediately selected. It has to work its way by, swapping elements. All right, so if you'll notice over here, right, the way this one's working, it's taking that smallest number 4, putting it in the first position. It's finding the next smallest, which is 7, putting it in the second position. Checking the next smallest and putting it in the third position. Okay, so selection sort can be written both ways. It can be written to look at the smallest elements and work our way up, or it can work the other way and find the largest elements and work our way down. Both are valid implementations of selection sort. You'll see here is some code for a selection sort. And can someone tell me how many swaps are being done? So first of all, let me teach you a Python trick if you don't know it already. This is how we do a swap. Okay, you put the 2 elements you want to swap on the left and the 2 elements you want to swap on the right, and you assign them. Okay, in normal code, like a Java code, you would use 3 lines for that. Use a temp, and then you put something in the temp, and you move something over. Okay, so Python lets you do it in 1 line. So can someone tell me per iteration of the outer loop, how many swaps are we doing?
Per iteration, n-1?
Well, per iteration of the outer loop, how many were we doing?
Well, 1 per iteration.
1 per iteration. And total, we're doing n-1. That is correct. Okay, how many swaps did we do in bubble sort per iteration?
n-1 per iteration.
Well, at most, it was n-1 per iteration. At most, right? Because it could be less if they're not out of order. And then if I have a lot of iterations, so that could be n times n-1 divided by 2. So the beauty of selection sort is we're only doing 1 swap per iteration, right? We find out where that smallest element is, and we swap it with the first position, and that's how we get it into position, right? So that's our selection sort. Okay, so the analysis is similar, but notice this line here. This is a very important line here, right? Only 1 per iteration. So n-1, which is order of n. Okay. Yes, let me, before we go on to insertion sort, let me point out, as I said before, I'm going to say it again now, selection sort is not stable. Why is it not stable? Let's look at the picture here. Let me show you why it's not stable. Okay, let's see if we have an example in this case why it's not stable. We might not have an example in this case. Maybe we will have an example. Okay, yeah, we have an example. We have a beautiful example of it right here. Okay, so why did we move the 4? Someone tell me why we moved the 4?
Because it's the smallest element and
The
you
smallest element, good. So we put it in the first position, and what did we replace it with?
10.
10, correct. Okay, and 10 was smaller and is smaller than 11, correct? Do you agree with that?
Yes.
Yes, but look what happened. 10 is now after the 11. You see that? Now, eventually we fix that, right? Eventually the 10 is going to go before the 11 down here. But at this point, the 10 and the 11 switched out of order with respect to each other. Okay, so that's an example of instability. Okay, eventually we fix it, but there is some instability that is introduced. Okay, so we had an example in that picture. All right, we're ready for our next sort, insertion sort. Right? What is insertion sort? So I like to give the analogy of cards, right? So how do you sort cards in your hand? Let's say you're looking at this card, you look over here and you find a place to insert it and you insert it. Then you take this card, you look, and insert it over here, right? So it's called insertion sort because you find the position where you should insert it. And let's look at a picture because that's clearer than whatever I'm going to tell you. So you look over here and we take our elements and we find where does it belong. Let's look at this 1 here, okay? Where does the 1 belong? So we look all the way to the left, and we find that it belongs in the first position. So all these elements need to move down. What happened in this case? Why are there no red boxes in this example in that one there?
Everything's already in order for that.
Everything is already in order. We don't need to move anything around to handle the 12. Same thing with the 10. In this case, we needed to, right? We needed to move the 4 down, the 3 down to make room, and we put the 2 in there. Okay, how many swaps happen in insertion sort? That's a trick question, by the way.
Is it n-1?
So we don't do any swaps, right? In the usual sense of a swap, right? Where you take 2 elements and you move them, swap them with each other. What do we do? You do move things down. Okay, we move things down one at a time, but we're not technically doing swaps in the usual sense. Okay, so let's take a look at this code here. We have a while loop. Okay, everyone see that while loop? And the while loop has 2 conditions, all right? One condition is to make sure we don't go out of bounds. We do not want to go out of bounds. What happens if you go out of bounds in an array?
You get an array out of bounds there.
You get something like an index out of bounds, array out of bounds error, right? You don't really like that. So we check to make sure that our index J, which is the position we're up to, is always greater than or equal to 0. Otherwise, we're going to get an out of bounds error. We don't want that. The other thing we do is we check, are we up to the right place, right? So is our key relative to the current position, is it good or not? Okay. If it's not, then we move everything down. So that's saying move everything down over to the right to make room. Okay, once we find the position we want to be in, we put it there. All right. Now, this is our example of the Sentinel. How many conditions do we have in this while loop?
2.
2. And if in comparison with the for loop in bubble sort and selection sort, how many conditions did we have?
We had 1 on those.
1, right? You're just checking, are we still in the range? Okay, so we now have twice as many conditions, compared to what we would expect another one. Now, not all conditions are created equally, all right? This is just checking the index, and this is checking the data. Data comparisons are generally considered to be more expensive as opposed to index comparisons, which are cheaper, okay? Now, that's not entirely true, because if your indexes are just numbers, let's say 2-byte numbers, and your keys, your values are 2-byte integers, then there's really no difference between checking an index and checking data. But data could be something complicated. It could be like a string or an object or something very large. So that's why we usually focus on comparisons of data, but I'm going to teach you a trick. Okay, so let's, do I have a trick here? No, I don't have the trick here, so I'm going to talk to you about the trick. The trick is we put a really small number at the beginning of the array, okay? Okay, so we're going to put the data in positions 1 through n, and in position 0, we put, like, let's say, a negative number. Why do we do that? Because that will ensure that the data that we have will never be smaller than that number, right? So we take a number that's not part of the data, that's for sure smaller than the data, we put that in the first position, and that guarantees that we will never go out of bounds, because whatever number we have will be bigger than the number in the first position. So basically, we can cut this out. Okay, that's a little trick we can do. And okay, so that's all right. Let me teach you another trick. I'm going to teach you another trick here, which is insertion sort with binary search. All right, so essentially what we're doing is we're trying to find where the number should go, right? Where does the 2 go? Where does the 5 go, right? What kind of search are we using to do that?
Well, we could use binary search. It's already.
I'm not asking what we can do. I'm asking what kind of search, what are we using? So in this picture or in the code, can't really tell from the picture exactly, but based on the code, what are we doing? Here's the code again. What kind of search is that?
Linear?
That's a linear search. But as you pointed out, yes, we could do a binary search. Why can we do a binary search?
The section we're trying to insert into is already ordered.
Right, the left-hand side, everything to the left of the current element is already ordered. So it's a perfect candidate for binary search. So why are we not using binary search?
Use the code
And you could write it, you could code it, you could code that. But what's the reason it's not as, amazing as it may sound?
But it doesn't change our time complexity anyways.
Why not?
Because it's only gonna add a O of n and we already passed O of it.
Yeah, well, I mean, if we were just doing, let's say log n for the binary search, and we did that n times, we would get n log n, which is better than the n squared. But here's the thing. Let's say, take this example over here, right? We put the 5 over, we know the 5 needs to go over there. Or we need to know the 1 needs to go over there. We still need to move everything down to make room. So even if you can figure out in log n time, like binary search, where it needs to go, it doesn't make room any faster. We still need to move the things down one at a time. So it's sort of debatable whether it's better or not. It's a nice little project to do, is to figure out, is it better or is it not better, okay? So that's another variation of insertion sort. All right, the next one is shell sort. Shell sort is sort of a complicated sort. It's sort of like an insertion sort, but we use gaps instead of gaps of one element, right? We're comparing one element to the next. We are sorting in gaps. So you see, we have the purple elements, right? We're sorting all the purple elements. We're sorting all the orange elements with each other. We're sorting all the green elements with each other. All right. So there, by the way, this picture is a little misleading. Okay, this comment here, sort every 5 element, is referring to what happens from here to here. It's not talking about this picture. It's going from here to here. Similarly, we're going from here to here. We're sorting every 3rd element, right? So we have the purples are the thirds. The oranges are the thirds. All right. There are many different ways of implementing shell sort. How you determine what those gaps are. Do I go from 5 to 3 to 1? Do I use bigger gaps? And it's very difficult to analyze, okay? So there's no one exact way to do it. And therefore there's no one analysis. So as you can see here, there are different estimates. Some say it's n squared, some say it's n over 3 to the 2, some say it's n over 4/3, some say it's n to the 1.5. Well, I guess that's the same as the 3 over 2, right? So there are different analyses depending on, again, what gaps you're using, depending on what the data is. In my experience, so you're going to do an exercise for home similar to what we did for search sort. I'm sorry, for search algorithms. And it often turns out that the shell sort does worse than the other simple sorts, not better. But again, it really depends. All right, so now we're going to do some math here. And hopefully you've seen this either in data structures or discrete structures before. But many, here, you know what? Let's, we're going to come back to this in a moment. Okay, let's do this first, and then we'll come back to the master theorem. All right, so yesterday we implemented binary search, and the day before we talked about it a little bit. And the recurrence equation for binary search is this. All right, anyone, can anyone tell me why? We discussed it a little bit on Tuesday.
After each one step that you complete, the amount that you have to search through is halved. So yeah,
Okay, so we said that you need to, determine if it's in the current position or to the left or to the right. And even though it's often coded in 2 steps, 2 ifs, in theory, it's supposed to be 1. So that's why we put a 1 here. Really, it should be 2. And then you have half of the work, either on the left side or the right side. So that's where this recurrence comes from. So we did one approach to solving this in that first lecture, but now we're going to use the master theorem. So the master theorem is used for divide and conquer algorithms. And it says that many divide and conquer algorithms are of this form. Okay, so they have t of n divided by something, multiply that by something, and then there's some function over here that represents the work in the subproblem. Okay, so we look at this binary search and we say, what is A? A is the coefficient. What is the coefficient here?
1.
1. And why is it 1? Well, it says here, because there's one subproblem. Why is there one subproblem?
We don't have to do half that's left.
You only have to do one side or the other, right? So you divide it in half, but you only need to process recursively one side or the other. Even if you do it non-recursively, it comes out the same. All right, fine. Now our B is 2. What is B? B represents the fraction of the original data that is the subproblem. So in this case, it's B is 2, right? It's 1/2 of the original problem. Why is it 1/2?
There's half of the elements left.
Half of the elements are left, either left side or the right side. And then we have the 1. Now the 1 is the same as saying n to the 0. So if you look back at the format, right, we're looking at what power of n is this f of n. So in this case, it's 1. 1 is n to the 0, so that means our c is 0. So we look at the 3 cases and we see, okay, the log b of a. So log 2 of 1 is what? It's saying 2 to what power gives me 1? 0. And c is 0. So that means we have case 2. Case 2. So we go back over here. Right, it's case 2 because log 2 of 1 is 0 and c is 0. So therefore our answer is n to the c, which is n to the 0, log of n. Okay, and notice the log, it's log 2 of n, but it doesn't really matter what base you use. It comes out the same. All right, so that's using master theorem for binary search. All right, we're gonna move on a little bit here. Our next sort is merge sort. We mentioned merge sort already a few times in this course, even though we didn't actually study it. Anyone remember what we said about merge sort?
Takes n log n.
Okay, it's n log n. What else did we say about merge sort?
Divide and conquer.
It's a divide and conquer algorithm. We also said that it can be used for external storage, right? Which again, we're not focusing on in this course, but if I need to sort data that I can't load into memory, put it all in the array, merge sort is better suited than, let's say, some of the other sorting algorithms. And we also gave it as an example of use of auxiliary storage, right? It uses, in addition to the original array, it has other array that it copies elements into when it's merging them. All right, so here is a picture of merge sort, right? So we break up our array into 2 chunks. That's where the auxiliary storage comes in, and we break that into chunks, and we break that into chunks until we have only 1 element each, which I obviously sort, and then we start to merge them back with each other, right? And sooner or later, we get the array in the order we want it. So let's look at the code for that. So here's some code for it. All right, sometimes this code is broken up into 2 pieces, right? You see this comment here where it says merge the 2 halves. So sometimes that will be broken out into a separate function called merge. Okay, so here's the merge sort part. Then we'll get to the merge. Okay, this part is the merge sort, and it says break up my array into 2 parts. Give them names. We're calling them L and R. Do merge sort on the left, do merge sort on the right, and then we merge the 2 parts. Okay, now in the merging of the 2 parts, you actually see 3 loops. Can anyone tell me why we need 3 loops to merge 2 subarrays with each other? So I'll give you a hint. Okay, imagine you have 2 lines of people, 2 lanes of traffic, right? And they're merging with each other. So what's the basic approach to merging?
To let one come through first.
You let one and then you let another. Okay, so in this case, we're always letting the smaller one next, right? The smaller one next. Okay, that's how we successfully merge. But what is going to happen necessarily? One of the lists is going to get exhausted before the other. They can't both end at the same time, right? One is always going to end before the other. So that's what this first loop does. It does the back and forth between them and figures out, okay, who goes next? So it's going through both lists and it's determining which one to copy into the target array. One of those is going to be done. The other one is not. So that's what these two loops are for. It says, okay, one of those lists still has some elements left. I got to merge those in. I copy those in. So that's what those two loops are for. Only one of those is actually going to get executed, right? So this gets executed, and then either this or that, okay? So one of those is going to happen. So let's do some analysis on that, okay? How much time does it take to do the merge? So the most work it could take is n-1. You know why? Because to figure out which element goes in first, we need to compare two things. To figure out which element goes in second, we need to compare two things. To figure out which element goes in third, we need to compare two things, right? We always need to compare two things. What about the last element? When I have one element left, do I need to do any comparisons?
No, since it's the only option.
The only thing left, so I have to copy that. So that's where we get to the n-1. Now, what could happen, let's just say the array was already sorted or somewhat sorted, right? And it turns out that of the two lists I'm merging, all the small ones are in one. So I take n-1 comparisons to get those in, and now I'm left with n/2 elements in the other one. I don't need to do any more comparisons because the other list is already exhausted. So you know what I do? I just copy them in. So in that case, I only need n/2 comparisons. Okay, what about the average case? So that was the best case. On average, it comes out we need about n-2. In other words, I'm likely to have, let's say, 2 elements left in one when I exhaust the other one. So that's where that n-2 comes from. It's a little bit of a question mark, right? Okay, so here is our analysis of merge sort. All right, we have 2 n divided by 2 plus n-1. So let's start with this. Where did that n-1 come from? It says on the bottom, but just to review,
That's how many comparisons you're gonna have to do.
that's the number of comparisons to merge the two lists in the worst case, and that's our focus is usually on the worst case. All right, good. What's this? And where did this n/2 come from?
To divide the list into two halves.
So I'm dividing in two halves, right? Each sub-problem in the divide and conquer is half the size. And where did that 2 come from?
You have two lists now.
I have 2 sub-lists. Good. And what about my base case? It's important, the base case. Why is that 0?
There's nothing to merge in an empty list, only one element.
All right, so if I have no elements or I have one element, it doesn't require any work, no comparisons to do it. All right, so that's a recurrence equation. Now we're going to use our friend, the master theorem. So the master theorem says I need to identify my A, my B, and my C. What is my A? What's my A?
2.
2. And what is my B?
2 also.
2. So I have log B of A. What's log B of A? I got a typo there. That's what I have.
1.
1. Good. And what is my C? Well, my C is, this is an order of n to the 1, right? So my C is 1. So I have log 2 of 2 is 1 and C is 1. So therefore that's case 2 of the master theorem. So I get n to the 1 log 2 of n, which is n log n. And that's how we know that it's n log n. All right. I think I have another, let's see what else I have here. All right, so here is a longer analysis. I'm not going to do that today. We're not going to do that today. We will come back to it. Okay, so let's see here. I do want to mention the Stooge sort before we go to our coding. All right, so the Stooge sort, it's also not one of the sorts I learned in school. When I started teaching this course in 1993, I didn't know what a Stooge sort was. I certainly didn't mention it. What is Stooge sort? Stooge sort is, it's a stooge. What is a stooge? Anyone heard of the Three Stooges? A little bit of pop culture there.
Idiot.
An idiot, a goof, right? So what is the Stooge sort? So I don't know if you could tell, but if you look at the code, we're sorting the first 2/3 of the elements. Then we are sorting the last 2/3 of the elements. And then we are sorting the first 2/3 of the elements. So there's a lot of overlap going on there. Now it works it actually works. It's not wrong. The problem is it's just doing a lot of work over and over again that it doesn't need to do. So it's an example of a divide and conquer. It's dividing into 2/3 here and 1/3 there, but it's just doing the same thing over again, right? Overlapping work, and that's bad, okay? So here is the recurrence equation for it, right? It's 3 subproblems. Each problem is 2/3 of the size of the original, so it's n times 2/3 plus 1. Why is it plus 1? Because if things work, there's only one swap that's happening here. Okay, so that's where that plus 1 comes from. Now let's use the master theorem for that. So what is A?
3,
3. And what is B?
2 over 3. 3 over 2.
No, 3/2, right? Because it's n times 2/3, which is the same as n divided by 3/2. So the B is 3/2. And why is C 0?
So this is just 1 n to the
Because
0.
it's n to the 0, so the 0 is our C. All right, so this is case 3 of the master theorem, right? Where the log base log base B of A is bigger than the C, and that comes out to be n to the log base 3 of 2, 3/2 of 3, which comes out to be n to the 2.7. So just to put this in perspective, how bad was bubble sort? Or how good was bubble sort, depending on your perspective?
N squared.
N squared. Selection sort was n squared. Insertion sort was n squared. Shell sort was somewhere in between n to the 1 and n squared, right? So this is worse, right? This is n to the 2.7 compared to, let's say, n squared or n log n, right? By the way, we didn't comment on it. So we gave a reason for all the other names. Why is shell sort called shell sort? What does that have to do with shells? Anyone like the beach?
Like you select from like
So
different.
the answer is, has nothing to do with the beach, has nothing to do with shells. The person who discovered it, if you want to call it that, his name was Shell. That was his last name. So they named the sort after him, okay? So nothing to do with how the sort actually works, right? So we're not going to get into the technique for the domain and range transformations. We'll do that another time. Okay, so this is a good point to stop. We're going to look for a volunteer to share their screen and be our coder for today. Preferably not the same one who went yesterday, not that excellent job, but we would like to share the wealth, give other people an opportunity. So anyone but Daniel. And again, there are 2 benefits to being the class coder. Number 1 is the whole class, you got 45 people, including the instructor, helping you debug your code. Otherwise, you're on your own. And number 2, I recognize that you're the class coder, and that works in your favor. So who volunteered?
It's Parminder.
Arminder, you're going to volunteer? Okay, great. So if you want to share, again, share your whole screen. If you need to close anything sensitive, please close any sensitive tabs and share your whole screen so we can go to the assignment. We can go to Google if we need to go to Google.
Okay, I'm just closing my tab.
I assume you have whatever we did yesterday, right?
Yeah, I have.
You're up to speed there. Okay, great.
You can see it.
I can see our course summary. So you want to, we want to see your PyCharm, and I think we're more or less done with looking at the assignment. So you can bring up the assignment anyway, in case we need it. Okay,
I see.
good. Good, but we need your pie chart. At this point, that's probably the most important thing. Well, we don't want a new project. We want the project that you were working on yesterday.
Oh, I did that in VS Code.
Okay, if you have it in VS Code, it works in VS Code?
Yes, it does.
Okay, so as long as it works, that will also be good. So I'm teaching you PyCharm, you'll teach me some VS Code, okay. Okay, wonderful. All right, so let's go down to the main. Okay, great. All right, so what we're gonna do now, at this point, you can delete lines 142 through 151. We don't need that anymore. That was just to get it going. Good. Okay, and what we're gonna do now is we're going to print our dict searches. Now, that was the last thing we did in class. Oh, can we do this? Okay. We're going to, you see that IDX2? Go to line 158. Okay, I want you to put an if after that statement. Okay, so in the next line, we're gonna put an if. You know what, do it after the end time. We don't wanna mess with our timing, so do it after the end time. And we're gonna
I
check,
recorded.
okay, here's what I want you to do. I want you to check if IDX2 is not equal to IDX1, or I'm sorry, we just called it IDX. It's sorry, colon, and the next line say print. We have a big problem. We have an error. How's that? We have an error?
No error.
No, I want you to put a quote. Right, we have an error. Can you write that, please?
Oh, okay.
We have an error. Okay, after the quote, we're going to put the name of the sort. So how do we get the name of the sorts? You could say search. Search is the sort function dot underscore name. I think we'll do it. Is that how we get it? Yeah, that's how we get it. Good. So that's the name of the sort. After the word error, sorry, an error in. The word in.
This word?
After the word error, put in, because it'll say in and the name of the algorithm, right? Good. You don't need the space, by the way, because Python will put a space automatically. Good. After the name there, put a comma. And then you could say actual or found. Let's say, no, put in quotes. Found, no, say found at. Yeah, and then after the quote, you don't need the space because again, Python puts in a space. Get rid of that space. Yeah, comma, IDX2. And then comma, expected at IDX. Okay, so what that's going to do is it's going to say if we find something in the wrong position, we want to know about it. All right, now, if you recall, go up to line 153. Okay, we have true and true. Who remembers what the true and the true are for?
If it was sorted, it had unique elements.
Okay, so the first one was for whether it's sorted, and what was the second one?
They had unique elements or.
Whether unique. Why is it important that they be unique? Why did we spend time to do that? What happens if they're not unique? The number 453 could be there more than once.
So that when you're searching, you don't know which one you want to return.
Yeah, so in other words, I might think I'm looking for the one in position 100, and I find another 453 in position 102. that's not really wrong, right? But it's gonna come out as an error. So by making them all unique, it ensures that we only find it in the exact place, okay? All right, but that's not what I really wanted to do today. What I want to do today now is print out the data frame. So if you look at line, did we make a data frame? No, we didn't make a data frame yet. Okay, so after the print statement, you could comment out that print because that's a yucky print. What I mean by yucky, it's not a nice format. Okay, so on the next line, you're going to say, we didn't make a data frame yet, did we? I don't think we made a data frame yet. Oh, right, we don't need to, right. Okay, PD is our pandas. Okay, so we're gonna say PD for pandas data frame dot set option, and it should come up. Set option is 2 words.
Okay.
Set option is 2 words, underscore. Why is it underscore? Go to the top. Go to the top, please. Did you import pandas? Okay, so if you didn't do that yet, you need to import it. So say imports. Maybe we didn't do it. I did 3 coding with my 3 classes. So I don't know what I did where. Import pandas as PD. It's an alias. Okay, so you say as PD, it's an alias. Very good. And that means you need to install it. So how do you install something in your Visual Studio? Visual Code. What is this thing called? Visual Code?
I'll check.
You might do a pipe install pandas.
Yeah, so in PyCharm, you can just click on it and it will do it automatically, but
I can open, I can paste all the code there, okay?
yeah, why don't we do that, okay? All right, so let's change the, replace all that. Paste, okay, go to the main.py and let's change the name of that on the top, on the tab. On the tab, yeah, rename. Call it assignment1.py. Okay, refactor. Okay, go down to the bottom. And now you click on that, click on that link there, that red underline. Click on it, please. Wait, hover over it again. It's not giving you the option to install. Install package pandas. And it will take a few minutes because pandas is very large.
Okay, it says it's installed.
Okay, great. Let's wait for that red line to go away. There we go. Go down to the bottom, please. Before we go any further, I'm going to let you do this on your own, but I just want to point out, if you go to the upper right-hand corner, can you go to the upper right-hand corner of that? You see over there, you see that yellow thing with the exclamation point, and you see another one to the right of it. You got 44 warnings and 26-week warnings. So I'd like you on your time to try to resolve most of those. Okay, if it says it doesn't like the word CSCI for computer science, that's okay, but you should try to clean that up. Okay, we want to use proper style. Okay, so let's go back to this set option. So you say pd.set option, and you're going to say quotation mark display dot max underscore rows. And then after the quotation mark, comma 500. Okay, so that says we can have as many as 500 rows. We're not going to need 500 rows, but it just says what the pandas data frame does sometimes is it cuts it off. Okay, do Control D on that line to duplicate it. Okay, and on the next line, do display.max columns. Okay, and you can leave that as 500 as well. Again, we're not gonna have 500 columns, but it just says don't cut out any of my columns. Okay, next line, do Control D. Okay, display dot width. I'm gonna make that 1,000. Again, I don't think we're gonna go anywhere near 1,000, but it just ensures that it's big enough. And the next line, very important line, DF for data frame equals. DF equals PD dot capital D for data frame. Click that first thing, data frame. And in parentheses, you're going to say from, I'm sorry, data frame dot, I'm sorry, not my bad, data frame dot from dict. You see, it's one of the options there. And basically what we're going to do is we're going to convert the dictionary that we made last class into a data frame so it presents nicely. Okay, so from dict searches. Good, click that. And after the parentheses, you could say dot T. Guess that's some kind of T, capital T as in Tom. Okay. All right. And on the next line, we're going to say print DF. We're going to print the data frame. Okay, we're going to run that. Okay, so we're going to try to just put another blank line there. That'll get rid of one of your warnings for you. Good. Okay, let's run it. Okay, you know what? Here's the problem here. Can you kill that, please? Red box on the left. Red box on the left. Okay. If you could grab lines 165 through 170, select those. No, 165 to 170. And do unindent. Okay, so I think you do shift like that. Okay, run it again. Okay, because we are doing it for every iteration. We don't need to do that. Just need to do it at the end. How many trials? Oh, okay, beautiful. Okay, so can you make your console bigger, the bottom part bigger, so we can look at a little bit? Okay, beautiful. Okay, so everyone see that? Okay, we have the sizes across the top. We have these searches on the left, and it tells us how they do. So, which is the fastest? Let's start this way. Which is the slowest for the 10,000? Okay, because the bigger the data, more data, the better picture we get. Which is the slowest?
Linear is the slowest.
Linear is the slowest. Okay, by the way, binary search doesn't appear to be much bigger than that. Okay, here's what I want you to do. Go back to the code and go to the size when we made the sizes. Okay, that first line there, and change that to 10,000. Okay, run it again. Okay, because the bigger the data, the more accurate the picture is. So it will take us a little bit longer. So you can have a, I don't know if you can have a coffee break, but if you have a water bottle, you can drink a water bottle. So we would expect that linear search is considerably worse than the others. So we would expect. While you're waiting, if you want, we could get rid of some of your errors. So if you want to click on that 3, the warning sign, we could try to help you work through your errors there. Yeah. Where do you get the array from? Oh, there's the array. Wait, something's wrong. No. The search needs to be indented. Lines 157 need to be indented, right?
Yeah.
157 through, no, including the time afterwards, all that. Okay, you need to kill that. Okay, so now we understand something very important, right? If you don't, sometimes the warnings are not just about, silly stuff. Okay, let's try this again. Okay, we can clean up the other stuff while we're waiting. Wants a blank line. Okay, good. All right, that is outside our control. It must be if there's some other L's and R's lurking somewhere. Okay, that's not in our control. Don't worry about that. Go on to the third one.
This is a habit from C++. In parentheses.
Yeah, I have that half from Java. All right, if you want, you could put a carriage return somewhere in that line, break it up into 2 parts.
I press enter.
Okay. All right, that's much better. How are we doing on our,
Oh, where did it go?
on the bottom? It should be somewhere.
Run. The bottom.
Click on the run
Run.
tab on the bottom. No, it's still taking a long time. Okay. If you want, you could kill it. We'll do something else to kill that. Kill, yeah. Okay, go up. I'll show you what you can do. You can, instead of range 1 through 11, change that to 1 through 6. And instead of 10,000, change it to 20,000. Okay. In fact, you know, what, let's do it even less. So let's change it to 3. Make it 4. Sorry, make it 4. Okay, let's run it again. You know where it's slow, by the way? It's slow in checking the uniqueness. It's slow for it to all right, you know what? It's not productive for us to wait here. So let's go click that red again. Click the red. Let's change it back to what we had before. So we change it to 1,000 and 1 through 11. Let's run that one more time. And we should get results pretty quickly. And again, linear search we expect to be slow. Okay, look at that. So this done linear search really was slow. All right, remember the first time we did it, the algorithm was wrong. So we can't go back. Okay, so this is much, look at that. Okay, look at linear search compared to binary search does pretty well. The interpolation search does even better. The jump search, not so good. And Python search, which is a linear search, but it does it using its own sort of back-end techniques. So it's better than our own linear search. Okay, so that's good. All right, so the last thing we're going to do today is the graphing. Okay, so we're going to make a function called, let's say, plot times. Yeah, so put it over there. That's good. Okay, fine. So let's do for, let's say as follows, for search, no, for is like a for loop. So for search, there you go. For search and dict searches, and we need to pass in the dict searches here. So you could pass in as a parameter. Remember what the dict searches is, as the names of our searches and how much time each one took. Okay, we're going to do a bar graph here. So let's do, we have dict searches. Let's put 2 more parameters there. Okay, one is called sizes, and the other is called searches. Okay, and we're going to have the first line. So before that, before the search and dict searches, say search num equals 0.
Here,
Before the for loop. Search num equals 0. Good, and if you could put spaces around the equals, please. Okay, now we need to import something else to do our plotting. So go to the top. And we're going to say import matplotlib, matplotlib, that's for plotting, dot pyplot, pyplot as plt. So we don't always have to say matplotlib, okay? And if you could click on that import thing there to install that matplotlib. Yeah. Okay, to install the success, let's go back down. Okay, so on your second line, after the search num, say PLT dot xtick, XTICK, that, okay, parentheses, bracket, J, for J in range, parentheses, len, parentheses, sizes. Okay, and you got your two parentheses there. Good. After the bracket, put a comma, and then say bracket str. No, bracket is a bracket.
Sorry.
Open bracket, that. str, parentheses, size. Okay, after the parentheses, say for size and sizes. So what we're doing here is we're looking at all the sizes. How many sizes do we have? We have 1,000, 2,000, up to 10,000. Okay, and then now we have for search in, not dict searches, but for search and searches. We're going to change that to for search and searches because we're passing in the searches. Good. Okay, on the next line, you're going to say search num plus equals 1. Plus equals 1. And again, we want to use spaces. Good. Next line. D equals. We like to have spaces there, please. D equals dict searches. Bracket. Search dot. Name. That thing there. Good. Okay, what that's going to do is it's going to get the data out of the search dictionary for the search that we're up to. Good. Next line. X-axis. X_axis. Underscore, not dot. X_axis. AXIS. Equals bracket J plus spaces, please. 0.05. Okay, what this is going to do is it's going to space them out. We don't want them all, we're making a bar graph. We don't want them to be all on top of each other. 0.05 times search num for J in range, parentheses, len, no space, parentheses, range, parentheses, len, parentheses of sizes. Good. Next line. That's going to space out the x-axis. Now we're going to do the y-axis. Y-axis equals bracket D bracket I for I and sizes. Okay, so what is D? D is the data we got from the dictionary in line 147. So it's going to be DI for I and sizes. Good. Next line. Okay, PLT dot BAR. We're going to make a bar graph here. Okay, parentheses, X_axis. So we pass in the x-axis to the plotting mechanism, comma, y-axis, we pass in the y-axis. Okay, comma, width equals 0.5, right? We're spacing them out. Width. Okay, width equals 0.05. Good. Next, comma, alpha equals 0.25.
Output,
Alpha, A-L-P-H, A-L-P-H equals 0.25. No spaces, sorry. This is where we don't use spaces, when we name the parameters. So, no, get rid of that space. And the alpha, you see, just follow its lead, okay? If it tells you get rid of the spaces, you get rid of it. If it tells you wants them. Comma, label equals. So this is where we tell it how to label the bars. Label equals search dot underscore underscore name. Okay, great. Next line, back up, unindent one. Unindent, good. PLT dot legend. Okay, that says we want to have a legend, right? Where it tells us what things are. Next line, PLT dot title. We want to have a title in our graph. Okay, parentheses, run time of search algorithms. Okay, great. Next line. PLT dot X label. Okay, parentheses, number of elements, right? So the label on the bottom and the X-axis is going to be the number of the elements. Okay, good. And next line is PLT dot Y label. And we're going to say time for 10 trials. Okay, because we're only doing 10 trials each. Okay, and in parentheses, you could put MS for milliseconds. Okay, inside the quote, parentheses, MS, yeah, to indicate that it's in milliseconds. Next line, PLT.SaveFig. And you're going to need to save the figure because you're going to need to hand it in as part of your submission. So you could say search, inside the save fig, you're going to give it a name. Okay, so you could say search graph. How about this? Assignment 1.
or in
In
quotes.
quotes, yeah. Assignment 1 dot JPEG or PNG. Assignment 1 dot PNG. Okay, good. And last, PLT dot show. Parentheses. Okay, good. Now go back to your main. And call that. Okay, so you could call plot times. And what do we need to pass in? The dict searches. And the sizes. And the searches. Okay, let's give it a spin. Okay, you got an error. I don't want to deal with it now. That means something in that division is off. You probably need to do some kind of int or something. But for now, just run it again, and it'll probably not happen the next time. You can check that. You put in some code that if it comes out to be 0. All right, let's try it one more time here. We don't have time to debug it now. So if you could run it again so we can check the graphing, and we'll try to figure out what it is. You probably need to just round up or something.
I think we can get the same error if we don't fix it.
Okay, I don't know, why did it work last time though? See, it depends on the data.
Yes, it's a lot.
That's what happened to my code.
Okay, so I guess we'll have to bite the bullet here. So which one is it? It's line 80. Is that the problem?
With relations. You set the position, you divide by 0 sometimes.
All right, so we're getting, that means that the key minus. Okay, here's what we're gonna do. Where is the close? I think we need the parentheses, put the parentheses after the ARRL. After the ARRL.
Yeah.
Keep going. Put another parentheses there. No. Keep going. A little more. No. Put the mouse where it was before. That ARRL, right after that, put another parentheses there. No, after it. And then get rid of a parentheses at the end.
Should I run it now?
All right, try running again.
That didn't fix the issue, by the way. I don't know if this is going to fix it.
Okay, we should be getting a plot.
Do you see it?
Yeah, but I don't see colors. Can you make it bigger? Maybe it'll be easier to see. Oh, you know what it is? We don't have enough trials, so the things are very small. You can sort of see it though. Can you make it bigger? Okay, so you sort of get the idea here, okay? Take, look at the 10,000. Okay, what color is that really tall one?
Near search.
Okay, so the linear search is really tall, right? Look at some of the small ones, right? You see the legend in the upper left-hand corner? So somehow your everything is very pale. Maybe that's the alpha. Is that what the alpha does?
Yeah, do we have option to change the colors?
Yeah, you can change colors, but I think it's the alpha. Change the alpha to a bigger number. You know, we could just leave it. Anyway, you get the idea there, okay? So again, that picture, which is now saved in your directory, you see, if you see on the left, you can get your picture back right there. So it's a little pale. I think you can control that with the alpha, 0.25. We could change that to a higher number, I think. But you can definitely see the difference, right? You can see that the linear search is taking a long time. Okay. All right, so well done. Thank you, Parminder, for coding for us today. All right, so just review, there's a Google form. I will be posting the link to you, but there's a Google form you can use for submitting this. So you're going to submit your code, your .py file, or if you happen to work in another language, you'll submit that. And then your console output, basically this chart there, that'll be in a text file, and your image file. So you're going to need three things to submit, and I will put that into the assignment. Okay, so you know what 3 things you need to submit. So I'll update the assignment to have a submission section if I didn't do that already. And you'll use a Google form to upload that. Okay, also assign some review questions in Top Hat about our lectures. So you can review those as well. Okay,
Is it okay that we have that divide by zero error? Because I didn't fix it. I think you just got lucky with.
I
yeah,
still have the
so
error as
you
well.
can, I mean, you can try to figure out, I mean, if we had more time or you want to stay on, I don't mind working with you to, should we try to fix it? And whoever needs to go, needs to go. Okay, so why don't, maybe we'll do that. Are you okay, Parminder, staying on a few more minutes? Yeah?
Yeah.
Okay,
Can I stop now?
what?
Can I stop the sharing?
Well, I'm saying if we're gonna try to fix it, then you can't stop the sharing. So are you okay with staying on a few more minutes?
Yeah, I'm okay.
You're okay with that?
Yeah.
All right, so let's try to understand what this is doing here. All right, so we're trying to figure out, so the problem is going to be in that ARR minus ARL. Yeah, so I guess the problem is if, no, but they can't be the same. How do we get a zero?
Is there anything that guarantees that L and R aren't the same?
So it's uniqueness, right? They can't be the same.
The L and R, like the actual variables L and R are the same number, so it's referencing the exact same element.
Oh, if R and L are the same. So why don't we, can we change that to less than? Oh, hold on a second. If they are the same, I guess we could do this. Put another if statement
Oh,
before that if, put another if statement that says if L equals R, and ARR of L equals key. Let's do this. Okay. Wait, not I, we need L. Equals key. Okay, let's you do if L equals R colon. If L equals R colon. Go to the left. Go to the left. No, if L equals R colon, go to the left.
Here.
After the R colon. Good. Now move that to the next line. If ARR of L equals key, return L, not L. If ARR equals the key, then return L. Else return -1. Okay, we should never get -1 because we're ensuring that the data is always there, but fine. Now, otherwise, if L equals R, so then we'll continue. Okay, so let's try that. Let's run that. Okay. I think we're good now. While we're making fixes, let's just fix the alpha. Let's make the alpha 0.5. Or make it 0.75 in line, I think that's what controls it. Line 156. Make it 0.75. I think the higher the alpha, the bigger it'll be. Someone wants to Google that for us. Just look at alpha plotting or something, alpha color or something, but you can run it.
Yeah, alpha is the opacity.
Okay, so the higher it is, the better, or the lower it is, the better? The darker, I should say.
Yeah, the lower it is, the more see-through it is. 1 is like
Okay.
0 will be.
All right, so that's a little better. You could even make it 1, but this is good now. Okay, so nice job. Okay, that's much easier to read. And you really see how the linear search takes it away. All right, the native search, the Python search, which is a linear search concept, but implemented better than we can implement it ourselves, is still high because it's a linear search model. And then we got these other things. What's that pink one there? Is that the Fibonacci? No, that's the, is that the interpolation?
No, the pink
That
one.
purplish one. What's that one that's pretty up there? Go back to the data. It's easier to look at the data. So that's the jump search. Pretty slow. Okay, all right. So great job, Parminder. I think we fixed that bug. We made it a little bit more readable. So thank you.
No problem.
Okay, everyone have a great weekend.
Thank you, Professor.
Take care. Bye-bye.
We don't need this anymore.
We are done.
Thank you.
Okay.